All right, members, you're welcome once again to my YouTube channel. This is Hyper, and I'm taking you through our last lesson in chemical kinetics, and we are going to look at the many effects, and then we'll look at those other reactions that, especially the hydrolysis of alkyl halides and the kinetics. Now, we are going to look at the effect of a catalyst on the rate of a reaction. When we say a catalyst, look at it as a substance which alters the rate of a chemical reaction, but remains chemically unchanged at the end of the reaction. This is the definition. And catalysts basically speed up the rate of a chemical reaction by providing an alternative route or alternative path of low activation energy from reactants to a product. It means that here also one can look at catalysts as acting as absorbing surfaces so that the reacting particles can collide on the same surface. But still, the main point is provision of an alternative route of lower activation energy. Low activation energy, meaning that when a catalyst is present within a certain reaction, the energy reactants must be possessing will be lower than the energy reactants must be possessing when the catalyst is absent. So we are going to look at the reaction profiles of both catalyzed and uncatalyzed reactions, but let's begin with an exothermic reaction. Now, during the in an exothermic reaction, of course, here we have reaction coordinate. And here we have potential energy. We know that for exothermic reactants, we have then shall have products here. So here is our reactants. Here is our products. Now, to this very same level, we shall have but still this one bringing to products. It is supposed to match here, supposed to match there. Now, this one, from here up to here, I can continue it here so that take this one from here up to here. Okay, then we have also this. So all this one, which is bold. At this point, we have an activated complex. For uncatalyzed reaction. Potential energy, I can measure it in kilojoules per mole. So this is an activated complex for uncatalyzed reaction. Whereas this one here, at this point, we form activated complex for catalyzed reaction. Now, from here up to here, we have activation energy for catalyzed reaction. Then, of course, from here, everything up to up there, we have activation energy. Let me call it EC, or let me just call it EA, just. So I can say EA represents the activation energy let me say for uncatalyzed. You can use different, but EA, but you can add on something, maybe EAU. Activation energy for uncatalyzed reaction, while EAC will represent the activation energy for catalyzed reaction. Very interesting. Now, from here up to here, we have the H, that's the enthalpy change. Now, the activation energy for a catalyzed reaction is lower, while the activated complex for uncatalyzed is higher. Simply because when a catalyst is present, it provides an alternative route of lower activation energy. That's why for low activation energy, rather for a catalyzed reaction, the activation energy must be lower from here up to here. So it must be lower for catalyzed. Reactants need little amounts of energy to react to products. So the activation energy, the energy possessed by the reactants products is not much. But you need to know what an activated complex is, because at any point we are saying activated complex. When we say activated complex, we are looking at that unstable intermediate, okay? So the activated complex refers to the unstable intermediate in which bonds of the reactant molecules are partially breaking, while the new bonds of the product molecules are partially being formed. We are going to look at the details of this when we start hydrolysis of alkyl halides, whereby rates of reactions are going to be helping us in determining the mechanism of a reaction. But for this point, what I'm trying to mean is that the activated complex is that unstable intermediate formed at this point, okay, in which bonds of the reactants are partially breaking, while the new bonds of the products are partially being formed or are partially forming. So that is what we call an activated complex. We're going to look at the details of that. Then, for the case of an endothermic reaction, for endothermic reaction, the reaction path still we shall have potential energy in kilojoules per mole, and here we shall have reaction coordinate. So now here, so here we shall have reactants, and here we shall have products. Then so that is what we are having, and of course, from here up to here, we have our enthalpy. Then the whole of this Let me call it EAU for unactivated. Then for this up to here, let me call it EAC. So at this point, we are forming the activated complex for unstable, rather for uncatalyzed reaction. Then for this point here, we are forming activated complex for the catalyzed reaction. Then, of course, this is the activation energy. EAC is activation energy for catalyzed. You can note it here. EAC is the activation energy for catalyzed reaction, while this is the activation energy for uncatalyzed. For uncatalyzed reaction. So that is what we are having. This DH, as we've already seen, refers to the enthalpy of the reaction. Enthalpy of reaction. Now, these catalysts can be classified. But before we classify catalysts, there can come a question here. There can come a question. Part A of that question. Using, it is for all viewers, using the same axes, draw a label diagram for energy reaction coordinate for a catalyzed and uncatalyzed reaction. Then B, state the difference in your diagram. Then C, state how a catalyst increases the rate of reaction. So that is the question that you can receive about so far what we've talked about. They can want you to draw the diagrams and explain them. So if they have not specified, it means you can draw for either exothermic or endothermic. But of course, after drawing them, you have to tell me that these diagrams differ in a way that the uncatalyzed reaction has a higher activation energy than a catalyzed reaction. As simple as that. Then the how a catalyst increases the rate of reaction, of course, it lowers the activation energy of the reaction by providing a reaction with an alternative mechanism or an alternative route or an alternative path of lower activation energy. As simple as that. So then, in addition to what we are covering, we need to go further and now know how these catalysts may be classified, right? Let's look at the classification of these catalysts. Now, the fact remains that some catalysts are homogeneous, while other catalysts are heterogeneous. When I say homogeneous catalysts, I'm trying to look at those catalysts that are in the same, okay, that are in the same phase with the reactants, right? So where you find that maybe if the reactants are solids, also the catalyst is a solid. So in that case, we say that that catalyst is homogeneous. Okay, so in that case, the catalyst, we say that it is homogeneous. But where you find the catalyst is in a different phase from those reactants, then we just say that that catalyst is heterogeneous. So we need to know the meaning of homogeneous and then the meaning of heterogeneous. That is when we can easily differentiate the two. Okay. Now, we have just seen that some catalysts are heterogeneous, the fact that they have phase different from that of the reactants, while homogeneous catalysts are the ones which are in the same phase as the reactants. So now, when you're talking about these details, or when you're detailing the explanation, we need to know how a homogeneous catalyst works and how a heterogeneous catalyst also works. All right, that is what I'm heading to. Now, a homogeneous catalyst, for it works by lowering the activation energy of the rate determining step by forming an intermediate. In other words, it is generally used for the reactions in aqueous solutions, meaning that a homogeneous catalyst works for those reactions in aqueous solutions. Then, for example, you can look at dilute sulfuric acid acting as a catalyst in iodination of propanol, or in a reaction between hydrogen peroxide and iodine, or rather iodide ions. You can look at oxidation of vanadium 3 ions to vanadium 4 ions by iron 3 ions using copper 2 ions as a catalyst. Okay, so those are the facts that I'm trying to talk about. All right. So what I'm trying to mean, well, we are saying that homogeneous catalysts, same phase with the reactants. Heterogeneous, different phase with the reactants, sorry. Now, we are saying that the catalyst, the homogeneous catalyst, works by lowering the activation energy of the rate determining step. At rate determining step, that is why you're forming an intermediate or that unstable complex or the activated complex. So we have said that it is generally used for the reactions that involve solutions. Now, here, the catalyst reacts with one of the reactants to form an intermediate, which reacts with the other product to form the final product that regenerates the catalyst. For example, if you consider reaction of A reacting with B to give the products of A and B in presence of catalyst C to form maybe products W. So it means that A plus B, they react to form W. But what you are saying, we are saying that in this case, a catalyst reacts with one of the reactants to form an intermediate. So maybe A will react with the catalyst C to form a certain intermediate SC. All right. Then we're also saying that that final product, okay, that final product SC reacts with the other reactant that had been left to regenerate the catalyst. So you are going to form the product W and reform, because A plus B was W, so and the catalyst C. So that is how these ones work. And amongst which examples is the using dilute sulfuric acid as a catalyst. We are going to explain the experiment that involves this in iodination of propanol, or in the reaction between hydrogen peroxide and iodide ions. Then we have also spotted another example, which is you look at esterification of ethanol using ethanoic acid in presence of sulfuric acid. Okay, those are all liquids. Then we are also looking at oxidation of vanadium 3 ions to vanadium 4 ions using iron 3 ions, but in presence of copper 2 ions as a catalyst. So they are very, very, very many. But for heterogeneous catalysts, they are normally used in transition metals. Okay, for example, during the hydrogenation, we use nickel as a catalyst. Use during cracking, during polymerization. So here it is the surface of the catalyst that helps in catalysis, whereby the reacting particles adsorb themselves on the surface of the catalyst, adsorbing, like attaching. They attach themselves on the surface of the catalyst, and thus the reactant particles collide on the surface of the catalyst. And those frequent collisions increase the kinetic energy with which reactant particles move, and thus increasing the rate of reaction. But here the main point is, for heterogeneous reaction, rather the surface of the catalyst is the one that speeds up the reaction, where all the particles collide from, the particles which are reacting collide from there. But for homogeneous, a catalyst takes part in a reaction, but you end up with it again. Because as per the definition, it remains chemical and changes at the end of the reaction. Now, this one is because, you know, in transition elements, we have got empty d orbitals possessed by most of those elements. So these catalysts work by using their empty d orbitals. And when they are doing so, they form weak bonds with the reactant molecules. Now, that one weakens the internal bonding of the reactant molecules, and thus increases the concentration of the reactant molecules at the surface of the catalyst by reducing the activation energy, hence increasing the rate of a chemical reaction. So in other words, just look at these heterogeneous catalysts as using their d orbitals, which are empty, to form weak temporary bonds with the reactant molecules. After forming those bonds, that weakens the internal bonding because those catalysts have already formed the temporary bonds with the reacting molecules. Therefore, the internal bonding of the reactant molecules will weaken, and that will increase the concentration of the reactant molecules at the surface of the catalyst, meaning that the more the concentration of the reactant molecules at the surface of the catalyst, the more frequent the collisions take place at the surface of the catalyst, and that increases the kinetic energy of the reacting particles, which thus increases the rate of reactions. For example, you can look at finely divided iron during the Haber process. You can look at nickel during the hydrogenation of alkenes. You can look at using platinum catalyst during the combination of hydrogen and iodine vapor, and more other reactions. Then there is other factor that I can cite out, and that is the factor of light, especially in photochemical reactions. Some reactions take place slowly or not at all in absence of light. For example, photosynthesis. Photosynthesis may not take place if light is absent. So for photosynthesis to take place, light must be present. All right, light must be present. So photosensitive reactions, for example, photosynthesis and formation of silver and silver salts that normally take place in the photographic film when it is exposed to light, their rates increase with the exposure to light. Okay, because sufficient energy or light of sufficient energy like UV breaks bonds in one of the reactants, creating a reactive intermediate from which products are formed. So here we are looking at light energy with sufficient energy, of course, breaks the bond. Remember, for a reaction to take place, bonds must be formed. From actual bonds must first be broken, and then new bonds formed. Now, during a photochemical reaction, one of the reactants, its bonds are going to break. And when the bonds are broken, there creates a reactive intermediate from which the products are formed. So that is what exactly takes place during photosynthesis, the composition of hydrogen peroxide, combination of hydrogen and chlorine, substitution reactions of hydrogen and methane by chlorine, formation of silver from silver salts, and many other reactions. All right, most of them which are organic, they follow free radical mechanism as they are proceeding. Then the final factor that I can cite out, the factor of pressure. Pressure, especially in gaseous reactants. When you increase pressure of the gases, it will push the gaseous molecules close together, increasing their frequency of collision, and thus they will react more rapidly. So we are looking at increasing the pressure within a container that contains gases. The gaseous particles are going to come closer together, colliding. The increased collisions, or the increase in frequency of collisions, will make those particles or the reactants to react more rapidly. So that is all about the factors. Now, we are going to look at how we can use something maybe which I've forgotten. Features of catalysts, that is something very important. Features of catalysts. Of course, catalysts are very specific to single reactions or to class of very similar reactions. It's not that all reactions will proceed in presence of vanadium 5 oxide. No, it is a certain specific reaction that is going to be proceeded with aid of vanadium 5 oxide. Still, catalysts can catalyze both forward and backward reaction at the same extent, and therefore they have no effect on equilibrium constant or equilibrium position. We are going to see this when we start chemical equilibrium as a topic. A catalyst does not affect the equilibrium position or the equilibrium constant, since they can catalyze either forward or backward reaction. When I say forward reaction, it's like when I have A plus B giving me C. In equilibrium reactions, especially chemical equilibrium reactions, the reaction should be reversible. So the rate of forward reaction by a catalyst will be the same as the rate of backward reaction. Meaning when I say forward reaction is A plus B forming C. Backward reaction is C decomposing or dissociating from A and B. So we are saying that catalysts catalyze both forward and backward reactions at the same extent. Another thing, we need to know that small quantities can cause a very huge increase in the rate of reaction. So it does not matter how much catalyst. And these catalysts can be easily poisoned by some other substances. For example, toxic heavy metals like lead, arsenic, cyanide, mercury, cadmium, etc. So that is it all about catalysts. And allow me to take you to determination. Allow me to take you to determination of a mechanism of a reaction in my other video.